Hello, I'm Gager Dominguez. I work with Jensen Hughes. I've been with them for 2 years now. I work in the Los Angeles office in California. I got my master's in fire protection engineering from Cal Poly San Luis Obispo, which is also located in Central California, for those who don't know.
And hi, I'm Arthur Gager. I worked in the LA office for 5 years. A couple months ago, I moved to the Boston office. But while we were working together in Los Angeles, we worked on a number of atriums, a number of airports, and similar large public spaces. During that time, we also worked on a number of prisons throughout the United States and closed amusement park rides with restrained occupants. Those are mainly the United States, but we also worked on them on some abroad. We found that there was not a lot of precedence or standardization for tenability criteria in these unique occupancies. Because of our work, we try to set personal standards and internal company standards for visibility, temperature, and toxicity, the typical tenability criteria. Exposure limits to temperature and toxicity are mostly dependent on exposure time, and the same approach for temperature and toxicity we saw could be used in standard buildings that we use in the atypical buildings. However, visibility did not vary with time, and we found that lower visibility criteria could be used for atypical scenarios. We also found that similar visibility limits could be used for prisons and amusement parks. This was interesting because these are very different spaces with very different occupant characteristics and overall characteristics. In general, there's two main types of smoke control systems. There's the smoke containment systems, which keep smoke in the area of origin and prevent it from going to an adjacent space. This includes pressurization or airflow methods. There's also smoke management systems, which will move the smoke from the area of fire origin to a different space. And the smoke management systems were the systems that we looked at for prisons and enclosed amusement parks. There's two different ways to analyze smoke management systems. That includes algebraic equations, which was the standard for a long time. The warm and, or I guess the upper and lower layers with the smoke interface height being maintained at a certain level above the highest occupied level. And there's also CFD analyses. Those allow users to have more, allow a more detailed analysis. Well, I have a clicker.
So we talked today about tenability criteria, and we need this tenability criteria in order to design an effective smoke control system. In order to understand this, it's important to understand the evolution of smoke control. So smoke control started in 1881 after the Ring Theater fire in Vienna. So during the late 1800s and early 1900s, there was a lot of theater fires with mass casualties. So this led to studying the smoke control. So the initial tenability criteria for the first smoke control system was to put vents above the stage just to allow smoke to vent if the stage caught on fire. The first successful use of that was in 1911 when there's a stage fire and this smoke vents above the stage allowed all the occupants to escape. So fast forward to today, we design our smoke control systems, as mentioned, with algebraic equations and CFD modeling, typically. In order to design this effective smoke control system, we need to determine our tenability criteria that we're going to use using these algebraic equations and CFD modeling. These different tenability criteria are determined, they're not black and white, and they're determined today using various guides and resources.
Yeah, the most common guide that probably everyone's heard of is the SFPE Handbook of Fire Protection Engineering. It has a lot of broad data that's really up to the user to determine what should be used for their occupancy. The Handbook of Smoke Control Engineering is a little more specific, and that goes over CO limits and those kind of tenability criteria for specific that could be used in general. It also contains information that can be used for specific occupancies. It suggests a visibility limit of 3 to 4 meters in someone's own home, 7 to 9 meters in a small atrium or university, or 12 to 14 meters for a museum with a complex design or a large atrium. And in all these cases, it's up to the engineer or designer to determine what's the applicable limit. Then NFPA 130, which was touched on by Andrew, talks about tenability criteria for fixed skyway transit and passenger rail systems. The tenability criteria in that document is contained in an annex. NFPA 92, the standard for smoke control systems, is very well known for smoke control. It currently does not contain any criteria or contain any tenability criteria. It's proposed to be added in future editions, though.
So because we don't have any of these, black and white tenability criteria, we take them from the sources that Arthur mentioned. So we all know that temperature and toxic gases are the direct cause of death in fires, but visibility is an indirect cause, as it can trap occupants in the early stages of a fire by relatively thin smoke. The presence of this smoke, obscures the light from windows, so occupants can't see as well, and they also can't see the light from the exit signs. So data from the SFB handbook, I don't know if it cuts it off a little bit, but they base this on different occupant characteristics and different building characteristics. For example, SFB handbook recommends for occupants who are unfamiliar with their surroundings, so us in this room, this might be our first time here, we don't know where all the exits are. A visibility of 13 meters is recommended by the SFB handbook. For occupants who are familiar with their building, whether it be your apartment or a school you attend constantly, a visibility criteria, you can't really see it, says 4 meters right there. So the SWA handbook also has guides based off of the building characteristics. So whether there's small enclosures and short travel distances or large enclosures with long travel distance. So for small enclosures, the SWA handbook recommends a visibility of 5 meters with short travel distances, and large enclosures with long travel distance, 10 meters. So this image up here is a kind of a typical prison layout. So in prisons, you have occupants who are familiar with their surroundings. They're typically located in small enclosures with short travel distances. So their visibility criteria for this could be in the range of 4 to 5 meters, per the SFP handbook. So to determine the visibility based off of CFD analysis, you need to know your visibility proportionality constant. For reflecting signs, this constant is 3. For light emitting signs, this constant is 8. So your proportionality constant is directly proportional to your visibility. So the higher the number, the greater visibility. It's important to note that even for prisons and amusement parks, if it doesn't require illuminated signs, you can provide those signs in order to reduce the effect that a smoke control system will have. So reduce the amount of CFM you need in order to see appropriately in that building. As Arthur mentioned, there's only one standard right now that actually gives you set tenability criteria, and that's NFPA 130, which says a smoke obscuration level should be maintained below the point at which a sign internally illuminated is discernible at 30 meters, and doors and walls are discernible at 10 meters. As we mentioned, NFPA 130 is very specific, and it's not applicable to, say, normal atriums or, for the purpose of this presentation, prisons or amusement parks.
Another typical tenability criteria is temperature. Temperature can lead to incapacitation or death in the fire victims in 3 ways: through hyperthermia, through body surface burns, or respiratory tract burns. Typically, respiratory tract burns do not occur without body surface burns, and hyperthermia is most likely to happen before either one of those 3, or any of those 3. So that's the typical tenability criteria used for temperature. The equation in the middle of the page is an equation that can be used to calculate hyperthermia, and you can see it's directly based on the exposure time. However, there are other factors that should be considered, such as the occupant's clothing and the air moisture content. In this graph, it can be seen that as exposure time increases, at the bottom, the temperature which will cause hyperthermia decreases. Also, dry air, which is the upper line, you can be exposed to a higher temperature dry air before hyperthermia is reached versus humid air. In these, but because of sprinkler activation, we have always used humid air when considering exposure temperature. This right here is a table taken from NFPA 130 for maximum exposure time before reaching hyperthermia. This includes a specific FED level, so and other safety factors in it. One thing to note for NFPA 130, there are some considerations such as not considering the effect of radiation. If someone's secured in a prison or in a secured amusement ride, they they could have a high, they could be more, they could have a higher chance of being exposed to radiation because they could not be, or possibly won't be able to move away from that fire. The last typical tenability criteria is toxicity. Smoke is the most lethal part of a fire, and most deaths in a fire come from inhalation. There are a lot of different products of combustion. This is impacted by the type of fuel and where the combustion occurs. There's also a wide range of effects to occupants because the different gases can be asphyxiants, sensory or respiratory irritants, and toxic gases. However, out of all products of combustion, carbon monoxide and hydrogen cyanide have the most researched and documented effects. They also account for the majority of fire fatalities. The effect of CO and HCN have on occupants is based on the time, and the exposure level. This roughly follows Haber's rule, but for these two gases, is not. It does vary from it, as you can see from the graph, because it's not linear. It's not linear as temperature increases. Regardless, the effect that these two gases have on human have on occupants and their combined effect can be used and calculated through an FED, or the fractional effective dose. Up top is I'm sure, just briefly, there's a basic equation for FED. This equation right here is an equation that can be used to calculate the FED for exposure to carbon monoxide and HCN. Typically, when tenability is being maintained, it's to some certain level for visibility, carbon monoxide concentration, or temperature. CO2 won't be in a high enough level that will have direct effects. However, CO2 can create induced hyperventilation. An equation to account for CO2 induced hyperventilation is on the bottom of the slide. NFPA 130 solely takes into account for its tenability criteria in the annex to NFPA 130. It just talks about CO. And this is a table from NFPA 130. You can see that there's a couple different values to be used for CO concentration. There's AEGL2, which is used more for general population, but it's more focused on the including susceptible individuals. Then there's an FED of a 0.3 or a 0.5. These can be used for more general population, with an FED of a 0.3 being used for more susceptible, a more sensitive population, and 0.5 being used for primarily healthy adults. So, through all, we did look into tenability criteria with the main goal for looking at prisons and the enclosed amusement rides, just because these are atypical areas. Smoke control has been required by the IBC in prisons for many code cycles. However, the 2009, there was a substantial switch. And the 2009 IBC required that specific prison spaces be provided with tenable conditions for exiting during a fire. This was a significant change because the previous code editions would allow for a pressurization system, or a system that was much easier to design. Prisons are unique spaces because they're very different from atriums, airports, or other large occupancies. As Gary said earlier, they're smaller with shorter travel distances, shorter rooms, smaller rooms. They're also spaces with controlled items. The amount of items, the amount of combustibles, and where those combustibles are is very controlled by the guards and the staff in the prisons. Also, the occupants are very different. Prisons are mainly comprised of guards and prisoners. That's the general population in the spaces that are required to be provided with tenability. In a fire, the prisoners are typically not allowed for free egress. And the guards during a fire, their main goal is not to egress. Their goal is their first objective is to assist prisoners in egress. So that's a substantial difference than normal spaces. As we said, there are a number of different prison layouts. This is one we worked on, and you can see this is a larger prison space. However, it's only 2 stories. There's a day room right here, and then cells around it. This is a kind of mezzanine level with cells, and there's a lower level with cells. These are the same layouts, except they're separated into segregation units. What's interesting is, although these are smaller units, they take significantly longer to evacuate something to definitely take into consideration for anyone who follows the IBC, because the IBC recently changed to requiring 1.5 times the egress time or 20 minutes, whichever is longer. So for tenability criteria such as temperature or toxicity, where the limits are very much based on duration, the approach for these two zones would change, or the possible results for these two zones could change. These are two other prison layouts that we've worked on. This is a dormitory layout where it's a decent sized room and all the occupants can move freely through it. But what's different with that space is, the space, it's still about 100 feet to an exit. So the space is still not that large compared to an atrium or an airport. This is one that we've seen a lot recently, and this is actually a medical building. So it's an I3 or a prison medical building. And this one was definitely more challenging because it had much smaller rooms where tenability was still required to be maintained. In this project, the gray areas are corridors, and we were required to maintain tenability in these corridors. And then looking at this is one the next slides focus on. So in this scenario, we had to maintain tenability inside this corridor system. The design fire was located right here, and you can see right away, tenable conditions were lost in the immediate space. And that was acceptable, but the goal was to maintain tenability in the corridor system for exiting during a fire. Right there is visibility, temperature, and carbon monoxide concentration. This is 200 seconds through the scenario. And you can see that visibility has started to fail or exceed its limits in this corner, but it's still being, CO concentration and temperature are still being maintained. This is 1200 seconds at the end of the scenario. These two slides did switch, or these two pictures did switch. I realized that a little too late. But this is visibility, and visibility has been exceeded in this one small corner. Despite that, the black line indicates where the limit's set. Despite that, CO concentration and temperature, the limits were still maintained. So we talked with the AHJ about the limited failure and it being only in one corner, not the full corridor, with CO concentration and temperature being maintained. So this was deemed acceptable for this scenario.
So along with prisons, we've also worked on a lot of amusement parks, both in the United States and abroad over the last couple of years. And I heard earlier today, tenability criteria, 10 meters for visibility, I think is pretty widely used, as well as FED concentration of 0.3. I've heard. Well, amusement parks pose a lot of very unique characteristics. Amusement parks in themselves don't require smoke control, but indoor or underground amusement parks typically have an atrium layout, which will require smoke control. But really, we're going to focus more on amusement park rides. So this is just a single-story dark ride in an amusement park. And while smoke control is not required by code, at least for in the United States, it's typically required by the area or by stakeholders or local jurisdictions. So part of the unique parts of amusement parks is that you have occupants who are restrained in a ride vehicle who are not able to egress freely during an evacuation or during an emergency. Another unique aspect of amusement parks, and this is from our project experience, is that the staff and nearby emergency personnel, so your nearby fire station or firefighters, are very familiar with the building and perform evacuation procedures at that building. Like I said, the amusement park creates challenges for the smoke control system just based off the nature of their operation. You're putting occupants in restrained ride vehicles where they can't egress freely. So there needs to be evacuation plans. From our experience, there's typically 3 evacuation plans, and the primary evacuation method is to cycle out your ride. You're going to stop loading people onto your ride. You're going to cycle out that ride how it normally would, and then you're going to egress your occupants off that ride in a normal fashion. So you need to have a smoke control system that's designed to maintain tenability for these ride occupants for 1.5 times that calculated time. Your second method is your manual evacuation. So typically your ride vehicles are going to have a manual release on them that need to be activated by the staff. So from our experience, the staff are trained in this evacuation procedure. They will go ride to ride and manually evacuate each person from that ride and walk them out of the building. So this can be much greater times than evacuation from a typical atrium, because you have to wait for somebody to come to you, take you out, and take you out of that building. The third evacuation procedure is it's a worst case scenario. While unlikely, it's a mechanical failure of a ride that puts the ride vehicle in an area or situation where the park staff can't get to it or can't evacuate those occupants. So emergency personnel need to come on the site, use emergency equipment, and evacuate these occupants. From our experience, this time can range from 30 to 90 minutes. So your tenability criteria is to maintain your tenability for 1.5 times this, which can be a very long time. Another unique aspect of this is that you measure your tenability limits at 6 feet above the highest walking surface. But for ride vehicles, you can have ride tracks that you can be trapped at the ground level right next to an egress path, or you can be trapped hundreds of feet in the air, which we've had on recent projects. So tenability needs to be maintained at these high levels. So the unique challenges to maintaining tenability for this is that your toxicity and temperature are based on your exposure times. So you can have occupants who are exposed for up to 90 minutes, at elevated surface, elevated heights. At elevated heights at the ceiling. Unfortunately, due to the nature of amusement parks, there's a lot of proprietary information, so I'm not able to show you guys the FDS slice files that I wanted to, but I can give you guys some of the data. So here we show, this is for a ride where the ride vehicle is at the ceiling of a dark ride, and occupants are trapped for a period of 45 minutes. You can see right here on the left is your visibility, which is your blue line. And you can see we get to below 4 and 5 meters of visibility. Now the orange line is your temperature, which gets to around 30 degrees Celsius. As we pointed out earlier, for 45 minutes, the SFP handbook and even NFPA 130 say that there needs to be, for 45 minutes, you need to maintain a temperature level of 40 degrees Celsius. So right here we show for 45 minutes, while our visibility does go to between 4 and 5 meters, we do maintain our temperature. Similar for CO concentration, as we said in the previous slides, SFP handbook references that for a 60-minute period, a CO concentration of less than 83 parts per million should be maintained. And this is for an AEGL2 limit, which is even more conservative than your FED of 0.3. So here again, we show that we maintain that while we are lower than that 10-meter visibility. We're at 4 to 5 meters of visibility. So through our project experience with both prisons and amusement parks, we found that temperature and toxicity, they're based on exposure times. And for prisons, you can have much shorter exposure times. And for amusement parks, you can have very, very long exposure times. But as probably most of you know, do FDS modeling, visibility is typically the first criteria to be lost during a performance-based analysis. From our project experience, a visibility of 4 to 5 meters has been used and accepted for both prisons and amusement parks. So in conclusion, as your tenability criteria become more standardized, the NFPA 92 committee is working on standardizing your tenability criteria, which is great for our industry. But special attention needs to be paid to the unique occupancies such as prisons and amusement parks, because these also have very unique tenability criteria. Questions?
Thank you very much. This is very nice, especially the case study part, but I would like to relate to the first part of the presentation when you were discussing tenability criteria and the visibility, which intrigues me a lot, because visibility is, in my opinion, quite abused in the fire protection engineering. First of all, the way how we incorporate visibility in our studies is an implementation of Lambert's Beer law, which is valid for a single monochromatic light source in uniform aerosol. And we use it for multiple polychromatic light sources in non-uniform aerosol, which is way away from its limits of its application. The second thing is that the theory that was the origination of this whole visibility concept we have today are the experiments by Jin in the 70s in Japan. And when you read the original papers, there is actually much more into it than what we are using today. For example, the K constant, which we all know is 3 and 8, is actually a variable that is dependent on the size of the sign and the luminosity of the background. And every single aspect of this theory has more to it than we actually realize at the moment. So when you add up all these errors together, the visibility concept stops being a sharp criterion. It's more like a very mathematical trick to show the density of smoke in a given point in a way that people can understand it. And I really don't like using it as a sharp criteria. What I like is to use it as an indication that something is wrong, like in the presentation about museum earlier when they showed that the visibility was broken and they figured out what happened, what was the reason, and they removed the reason. So in my work, when I do with special areas like you were presenting, and I have this visibility which usually breaks first, I rather not use it as a sharp boundary that it's wrong. I rather find another tenability criteria that goes second and then search for the reason why it happened, because I personally don't really trust visibility that much. Thank you.
And that's kind of part of our presentation, is that, you know, in our experience, visibility is by AHJs, is they often look at that first and they want that to be maintained. And what we're trying to show is that, you know, our toxicity levels and our temperature levels for 90 minutes, you know, we're going to have our occupants are going to be safe. They're just not going to be able to see on this, you know, and the visibility data we're using, like you said, the data from the 1970s, the data from, you know, the visibility for familiar and unfamiliar areas, that's taken from a test where they put you in a, they put occupants in a room, they filled it with smoke, and you put basically a stylus through a hole, and then you had the people who were doing the experiment, then they went inside and they performed better, and they were saying, well, the people who knew what was happening in the experience were more familiar with their surroundings than those who weren't. So I do agree with you. You know, the data is not solid, and it's what we've used from the SFP handbook, and there needs to be more data. But really what our presentation is showing is that our toxicity and our temperatures are maintained, and, you know, because our visibility drops to 5 meters, that shouldn't be a failure.
Another question?
Thanks for the presentation, really nice. Just a question about, like, if you guys have any recommendations on how to go about selecting carbon monoxide criteria, because you can see it ranges in your table from 20-something to 2,000-something ppm. Any kind of general guidelines on how you go about that?
Yeah, I mean, a huge factor is the duration of the exposure. And using something like AEGL2 would be for if you know there's going to be occupants at risk. We've almost never seen carbon monoxide being the failure criteria, because we are, like we said, we are maintaining visibility, which is typically the first thing to be, typically the first tenability criteria to be exceeded. And when we were unsure, we try to go with the most conservative approach. One drawback that we have seen to using the most conservative approach, such as AEGL2, when you look at just that, and that might be getting close to being maintained or close to being exceeded, if the AHA or you start to consider the effect of other gases, such as HCN or CO-induced or CO2-induced hyperventilation, although you're not exceeding that AEGL2 limit, if you use something like AEGL2 in an FED equation, and then you start to consider other gases, you'll exceed that tenability limit. So there's a lot of data out there, and trying to consider what's the best for your case. And when we deal with AHJs, not really sure what questions will come up.
Just a quick second question is, I think NFPA 2019, I saw on the website they're looking for suggestions of changes. Have you guys gone through the document closely and kind of seen, well, this seems a little bit unreasonable, any kind of proposed changes that you might find?
No, we haven't gone through NFPA 219, was it?
130, sorry.
Can you repeat your question now that it's 130?
Yeah, it's open in the year 2019. They're opening for suggestions. I saw on the website. Is there any kind of changes that you might propose in that document that you kind of come across thinking that it's a little bit unreasonable or might need to be modified?
So NFPA 130 is a very specific, and really we've been in more contact with some guys on the NFPA 92 committee, and that's really where it looks like, in the next edition that tenability criteria will be pushed, especially it'll most likely be pushed into the annex. But I can't really speak on behalf of the NFPA 130 because I don't have enough project experience with that specific, application. But it's important to note that right now they're the only standard, at least that I'm aware of. I'd love to hear if there's another one from our U.S. perspective, that it's the only criteria or standard that actually gives set tenability criteria.
Thanks a lot.
Any others? Okay, well, thanks. Thanks, guys.